Hello everyone. In this video, we will learn to define the internal energy of a system, to differentiate between heat and work done, 3. Determine the change in internal energy of a system from heat and work done, 4. Determine the sign of the heat and work terms in the first law of thermodynamics. As mentioned in the introductory video, in this chapter, we are going to define various laws of thermodynamics. Specifically, we will discuss first, second, and third laws of thermodynamics. Each of these laws introduces a special property that is related to the system. The first law of thermodynamics introduces a concept called as internal energy of the system. The internal energy of a system is the sum of potential and kinetic energies of all the particles present in the system. We represent the internal energy by letter E. We know that the kinetic energy of a particle is by the virtue of its motion. Therefore, all the particles that are moving, vibrating, or rotating have kinetic energy associated with them. The potential energy is by the virtue of its position or composition. And there are different types of potential energies such as gravitational, chemical, nuclear, etc. Let us say we have a sample of ideal gas in a rigid cylinder with a movable piston, and we need to measure the internal energy of this system. It is very difficult to measure the absolute value of internal energy, as there are several particles in the system and each particle has several protons, electrons, and neutrons inside them. So, we have to measure the kinetic and potential energy of all these particles and add them up to calculate the absolute value of internal energy. So, we can say that it is not easy to calculate an absolute value of the internal energy of any system. Fortunately, we are not interested in measuring the absolute value of internal energy. What we are interested in is the change in internal energy of a system. Let us assume the internal energy of a system in state 1 is E1, and the system undergoes some changes and its internal energy changes to E2. Now these changes could be change in pressure, change in volume, or any other changes. What we are interested in is the change in internal energy represented by delta E. The delta E of the system is equal to internal energy at the final state E2 minus the internal energy at the initial state E1. The change in the internal energy of a system can be measured, unlike the absolute value of the internal energy. Measuring the internal energy of a system is like measuring the volume of an ocean. It is very difficult to measure the entire volume of an ocean because there is too much water to measure. However, if we add a glass of water to the ocean, we can say that the change in volume of the ocean is 1 glass. If the initial internal energy of the system is greater than the final internal energy, as the system moves from its initial state to the final state, it should lower its internal energy. Therefore, the system loses energy to the surroundings in the process, and the delta E is negative. If the initial internal energy of the system is lower than the final internal energy, as the system moves from its initial state to final state, it should increase its internal energy. Therefore, it gains energy from the surroundings and delta E is positive. So, the system can lose energy to surroundings or gain energy from the surroundings. The next question is, in what ways a system can gain or lose energy? In other words, what are the factors that change or alter the internal energy of a system? The energy transfer between the system and surroundings can occur in two different ways. The energy can be transferred in the form of heat flow between the system and surroundings, or the energy can be transferred in the form of work done between the system and surroundings. Let us now define what each of these terms mean and discuss how they change the internal energy of the system. Heat is a form of energy that is transferred when there is a difference in temperature between the system and surroundings. Heat always flows from a hotter substance, that is, the substance at a higher temperature, to a colder substance, that is, the substance at a lower temperature. Heat is represented by letter Q. For example, we have an iron block at 25 degrees Celsius which is placed on a hot plate at 100 degrees Celsius. Since the temperature of hot plate is greater than the temperature of iron block, the heat flows from the hot plate to the metal block. Assuming the metal block is the system, we can say that the heat flows from the surroundings to the system. And when heat flows into the system, it increases the temperature of the system. The particles inside the system move or vibrate faster, therefore increasing the kinetic energy of the system and consequently its internal energy. Conversely, if the heat flows out of the system, it decreases the temperature of the system, which in turn leads to reduced motion. The reduced motion lowers the kinetic energy and consequently its internal energy. Next, work. Work is the energy transferred when an object is moved by a force. When the work is done on a system by the surroundings, the internal energy of the system increases. And when the work is done by the system, its internal energy decreases. For example, if you take a metal wire and rapidly bend it back and forth, you will notice that the wire gets hotter. That is, its internal energy increases. The increase in internal energy is because of the surroundings doing work on the system. Conversely, if the system does work on the surroundings, it uses its internal energy to do the work. Therefore, the internal energy of the system decreases. For example, if you go to gym and lift weights, the system, that is you, are doing work on the weights, that is surroundings. Therefore, you lose your internal energy or you are doing some work at the expense of your internal energy. Let us now consider a system whose internal energy is being changed both by work and heat. In such a case, the change in internal energy of the system is affected both by the work and heat. We can represent this by writing a mathematical equation. Delta E is equal to Q plus W, where delta E is the change in internal energy of the system. That is, delta E is equal to E final minus E initial. Q is the amount of heat transferred to or from the system, and W is the amount of work done by or on the system. All the quantities are measured in the units of joules, kilojoules, or calories. This equation is called as the first law of thermodynamics. The first law of thermodynamics is also known as the law of conservation of energy, which states that the energy is neither created nor destroyed. It can only be transferred from one form to the other. When the internal energy of the system is lost, it is transferred to the surroundings in the form of heat or work, or some combination of heat and work. The internal energy lost by the system is exactly equal to the internal energy gained by the surroundings. That is, delta E of the system is equals to minus delta E of the surroundings. Next, let us discuss the sign conventions for the first law of thermodynamics. A thermodynamic variable always consists of two parts: a number, which gives the magnitude of the change, and the sign, which gives us the direction of the change. In chemistry, we always use the system's point of view to represent the sign of a thermodynamic variable. That is, anything that increases the internal energy of the system is given a positive sign, and anything that decreases the internal energy of the system is given a negative sign. For example, if 10 joules of heat flows into the system, we represent Q as plus 10 joules. The number 10 represents the magnitude of the heat transferred, and the positive sign represents that the heat flow is increasing the internal energy of the system, which means the heat is flowing into the system. Conversely, if 25 joules of work is done by the system on the surroundings, then W is equals to minus 25 joules. The negative sign suggests that the work done decreases the internal energy of the system, which means the work is done by the system. So, we can use the following strategy to determine the sign of variables. You assume yourself as the system, and anything that increases your internal energy has a positive sign, and anything that decreases your internal energy has a negative sign. If you absorb heat, Q is positive. If you release heat, Q is negative. If you do the work, you will lose internal energy, therefore W is negative. If someone does work on you, W is positive. When doing arithmetic calculations, it is very important to keep an eye on the signs of thermodynamic variables. Let us now do a couple of examples. Let us do an example. A hot metal block is placed into a cup of cold water. What is the sign for Q water and Q block? Pause the video here and try to answer this question. We learned earlier that the heat always flows from a hotter object to a colder object. In this case, the metal block is hot and water is cold. Therefore, the direction of heat flow is from metal block to water. So, the metal block is losing heat and the water is gaining heat. The internal energy of metal block goes down as it loses heat. Therefore, the Q of block is negative and the internal energy of water goes up while it absorbs heat. Therefore, the Q of water is positive. Example 2. Water turning a turbine in a hydroelectric power station. What is the sign of W water and W turbine? Pause the video here and try to answer this question. In this example, water is doing work on the turbine. Therefore, water loses its internal energy and W water is negative. Work is done on the turbine, therefore W turbine is positive. A sample of gas does 25 joules of work on its surroundings and gains an internal energy of 40 joules. Does the sample of gas lose or gain heat in this process, and by how much? Let us now write down what is given in the problem. The sample of gas is the system and it does 25 joules of work on the surroundings. Whenever system does work on the surroundings, it does so at the expense of its internal energy. That is, the system loses its internal energy when doing work. Therefore, using the sign convention, we can say that W of the system is minus 25 joules. During this process, the internal energy of the gas is increased by 40 joules. That is, the delta E is equal to plus 40 joules. And we need to find if heat is lost or gained during this process and by how much. We know that according to the first law of thermodynamics, delta E is equal to Q plus W, where delta E is the change in internal energy of the gas, and we know that in this example, the internal energy is increased by 40 joules, that is, delta E is plus 40 joules. W is the work done by or on the system, which is given as minus 25 joules. Q is the amount of heat transferred to or from the system, which is what we need to calculate. Plugging in the values of change in internal energy and work and solving for Q, we get Q is equals to delta E minus W, that is plus 40 joules minus of minus 25 joules. If we do the math, we get plus 65 joules. So the system should absorb a heat of 65 joules during this process. Again, the positive sign represents that the internal energy of the system is going up during this process. Therefore, the heat is absorbed by the system.